All right, let's get started. So, good news. I've heard that heating is turned on campus. Bad news, it's not here. It's warm in my office, so that's good. Okay, so today we'll finish up this NC, and I've been promising email for a few lectures now. This time we definitely will cover it, and hopefully we'll get into a little bit of the next homework, which is a web proxy. So we'll at least look at how a web proxy works, which is really simple. Okay, so I realized, I don't know, on the way home or something that I was being silly here. The compilation error probably will go away now, but yeah, but that wasn't the silliness. The silly stuff was this. I don't need this list of client file descriptors. There's not really any point in that. They're just going to be integers anyway. And they're always going to be only one of every integer. Right? It'll be number 4. I can see it many times maybe, but only one at a time. So there's no point in having this. What am I going to have in there? They're going to be 0s and 1s and 2s. Actually, those are not going to be there. 3s and 4s and 5s and 6s. All right. So that seems unnecessary. What I can do is just keep a number of, see how many file descriptors I have total. And then the rest will be in my read set. If I've added something to the read set, well, that means it's a file descriptor I'm interested in. And if it's not in the read set, well, then it's a file descriptor I'm not interested in. So I think we'll just do it that way instead. So, let's see here. So where were we? Actually, maybe we should review, just briefly. So the goal here was handle multiple incoming sockets. Right? So you have clients coming in, they're wanting to talk to the server. We're making, it's more like a chat server or something now. It's not NC anymore. And now we want to be able to receive messages from any one of these clients, and also accept new incoming connections. So the first thing we did here was we added the server socket to the read set. So now Select knows that, oh, we're also interested in incoming connections. It's not really much of a read, like a socket coming in, there's no data coming there, but for a server socket, that's how we interpret it. We think of that as a read, so we put it in the read set. It's better than write or error, at least. Put it in the read set, and then we're going to have, whenever a socket comes in, the server socket will be in the read set. So we got that down here. Move this around a little bit. Okay, and then for all the other ones, it's going to be, I don't know, oh yeah, that's standard in. So for all the sockets, we want to run through all of the clients that could be there, right? We want to see, did we get anything from them, and if so, we receive it and print it out on standard out. Okay, so why am I spending so much time on select? What do you think?
You mean in lecture?
Yeah. Why so? I mean, select. We're now on the 3rd lecture on select here.
It's probably very important.
In part, it's really complicated, and in part, it's the only way to do multiple clients with a single thread or a single process. So you end up using this all the time, and it's not just for sockets. It's also if you're talking to disk. Right? Disks are really, really slow. So actually, they're much slower than the network in some cases. How long can you go, do you think, in terms of a network, within the time it takes to look something up on a disk? We want to read a block from disk. How far away can the destination be on a network if you instead want to go fetch it from them, and maybe they have it in memory? No. So I'm saying, okay. So we have two options here. I was just, it's a side point here, but it's good to be able to have these kind of back of the envelope calculations, right? So we have two options, right? There's something we need to fetch. It's a piece of data. It's like a kilobyte. Nothing to worry about. We have it on our disk. But there's also this other computer that has it in memory, sitting somewhere else. How far away does the computer have to be for it to be worth for us to look it up on disk? I'm saying disks are slow.
Out of Chicago?
Out of Chicago. Okay.
But wouldn't it depend on the network? Like if it was a fiber, it would be faster.
Yeah, to some extent, but not really, because this is so little data. Let's change it. It's not a kilobyte. It's only a few bytes. Even a kilobyte is nothing, right, on a regular link. If you still have dial-up, then you're in trouble. For many other reasons, maybe. Okay, so the limiting factor for a network communication is the speed of light. So the speed of light is 300,000 kilometers per second. How long does it take to look something up on disk? About, come on. 15 milliseconds, okay, any other guesses? We got some nanoseconds over here. Milliseconds, nanoseconds, so there's a factor of 1,000,000 there. So we're okay. Any other guesses? Anyone for micros? Micro, okay. Anyone for seconds? No? Okay. Yeah, so looking things up on disk is slow. Nanoseconds is fast. By all computer measures, nanoseconds is fast because every cycle is going to be on the order of nanoseconds. Right? Maybe a half nanosecond, but still. So milliseconds is the right answer. It's about 8 to 12 to maybe 15 sometimes milliseconds on average to get the arm to move over to the right place and then wait for the disk to spin around. All right? So you don't know how fast the arm is. Let's ignore the speed of the arm. We know how fast the disks spin. Many of you at least know how fast the disks spin. It's the kind of geek thing you do. Remember those things, right?
5,200 RPM.
Yeah, 5,000. Did you say 5,200? I never heard of one of those.
It was 5,200.
5,400. Geek cred over there. 7,200 is another one. Yeah.
10,000.
Maybe, okay, yeah. You can even go up to 10,000. So that gives you what? How long does it take for the disk to spin around until you get to the right place? All right. So say it's, to make it easy, say it's 6,000 RPM, right? That's per minute. So that means 100 revolutions per second, right? So how long until it gets around to where you are? 1,000 divided by 100 is not 100. Let's try again. 10, right? So you got 1,000 milliseconds per second. It goes 10 times around every time. Takes 10. In the worst case, it takes 10 milliseconds before you get all the way around. But of course, in the average case, you're going to be only halfway around. So 5 milliseconds for that, and then it'll take you a few more milliseconds to get the arm to the right place. So that's on the order of how long it takes. Okay, so we're almost there. Now, how far can we get with the speed of light call it 10 milliseconds for ease of arithmetic, right?
300,000 per second.
300,000 kilometers per second. It's the speed of light. In vacuum, to be honest. And in 450, we'll learn that the speed of bits in the internet is not quite this fast, but it's pretty close.
It's still like 45,000 kilometers the time it takes to look at this.
Let's see. In the, I missed that.
It's probably, I would guess, about 45,000 kilometers is how long it would take for the disk to ship this thing out, roughly.
Yeah, okay, so let's see. So looking something up on disk, we called it about 10 milliseconds. So that means we have, so that 10 milliseconds, that's a hundredth of a second, right? So that's 30,000 kilometers. That's far, right? Wait, divide by 100. 3,000 kilometers.
But that was, by 100, it's 1 millisecond.
1,000.
A millisecond, there's 1,000 of those in a second.
Oh, okay.
Yeah. Please, let's get this straight before we graduate. I don't want to embarrass the university here. Okay, so there's anyway. Yes, please practice the orders of the 1,000 orders of magnitudes and also the factors of 2. They're very good to know. Factors of 2 up to 16 bits. All right. After that, rough order is enough. Okay, so 3,000 kilometers is how far we can travel. So how far away can the machine be? In the best case, we have a really fast, nice network. Exactly. So it's actually round trip. So 1,500 kilometers round trip, which is how many miles? 1,000 miles. Okay, so the machine, in the ideal case, could be 1,000 miles away, and it'll be faster to go fetch those bytes over there than to fetch it from our disk. Yeah.
So anywhere in the Midwest?
Pretty much anywhere in the Midwest. Yeah. Okay, so in practice, it's probably not going to be quite like that, but if we're like a rough order of magnitude kind of estimate, call it 500 miles. So that's still going to get you most of, probably all of Illinois, right? And yeah, not that there's that much around here. Okay, so that gives you an idea of how slow disks are, or maybe how fast speed of light is. This all changes if you want to fetch a lot of data. All right? If you want to fetch, say, a gigabyte, it's a whole different story. Now it depends how fast your network connection is, and usually your disk connection, the connection that goes to the disk is going to be much faster than the connection that goes to Wisconsin. So for large things, it's still better to fetch it from disk. Okay, I don't know how we got to that, but I like these things. Okay. Right, so we're connecting to all these clients. That was the point. You can even, if you're talking to the disk, you're doing things, you're talking to clients, and they're in a hurry, right? And you say, yeah, okay, let me just go fetch this from disk for you. That's no good. Because now the disk is going to take several milliseconds before it responds. You can't just sit there and wait for the disk to respond while you have hundreds of clients coming in asking for more service, right? So in that case, you're going to have to request the read, do a non-blocking read, and then wait until, with select, wait for the disk to come back. So the file descriptor, wait for that file descriptor until it's ready to read, and then you get something and you send it off. Right? This is very important to make things fast, and that's what we do in systems programming. Right? Okay, so now we have, the idea was here, we want to keep a count of how many clients we have, or that is the highest file descriptor that we're interested in. And then we'll just loop through all the file descriptors and see if any of them have anything for us. So whenever a client comes in, I'm just going to accept it like this. So now we have the file descriptor for the new client. And of course we want to stick that in the read set. And let's not call this client count. Maybe we'll say max client. If new client is bigger than max client. Okay, I'll change this max client. All right, so now the idea here is our read set not only keeps track for select, it keeps track for us as well of which clients we are currently talking to. It's just a bit set, so a bit array, so it doesn't matter. And we don't, these FD set functions are handy for us as well. Okay, so now we want to see here, I suppose we can, doesn't matter actually, we can just go like this. So if client C Okay, do you see any problems with this?
Starting at 0.
Starting at 0. So now I'm looking at standard in. That seems like a problem. And then standard out's going to come, standard error. That's not for us. So we might as well start at 3 here because that's where our clients start.
You also zero simplifying count when should be max clients.
Oh, very good. Okay, so now we're looping through all the clients. If the client is in the ready set, if they have something to give us, then we will write it out and then start over. That looks pretty promising. Let's see if we can get that to compile. 54. Oh. Oh. And new clients. Okay. So now we should be able to run this. Let's try it out. Now we need a couple more windows so we can talk to it. One more. Come on. There. Okay. That didn't work. Isn't it the 8080 we were listening to?
Yes.
Double check this. 8080. Did we do a listen? Yes, we did. So maybe we should see if something happened in here. Try that out. Ah, okay, so we're in pretty good shape. Oh, what happens if I say something here? Ah, we don't have a way to write anymore, do we? So here on standard in, it doesn't actually write anything at the moment. We don't have any clients to write to, and we haven't even written the code for that yet. Okay, so for some reason when I type stuff here, it doesn't come out. Oh,
No, it's the same. You already typed here.
oh, I typed here there? Okay. Ah. Okay. So for some reason, this thing here is not working for us. Let's see. So max client, new client is bigger than, so this should be good. New client is in the read set. That should be good. Oh, I'm starting at 3. Oh, that should be fine.
Oh, we're never incrementing max client.
We are here. So, okay, let's check this out here.
Well, we start max client at 3, or we start max client at 0.
Yeah, so that means,
Until 3 is less than 1.
so new client is 3, most likely. So that'll be larger than max client, so that should be, let's see if our loop is coming in here. So you're going to be doing all this for your homework, so we might as well get this straight here.
Should it be less than or equal to max client?
Oh, okay. So this is not less than or equal to, oh, that doesn't matter. The assignment wouldn't make any difference if it's equal.
We end up on C is less than, but apparently not. Less than or equal to.
Oh,
I don't think that's it. That's just getting to check the client.
so why did we get, what? Why did that even run? So max client must not be 3 then. Max client must be 4. Where's our 3? Ah! There we are. The select socket is number 3. The server socket is number 3. So number 4 is what's coming in here.
So you need less than or equal.
So exactly, there's the bug. Less than or equal.
They started at 4.
That's not a bad idea at all. Whoever said that. Let's just put that in here too. Okay, so that should be much better. Ah,
There we go.
cool. Okay, so let's try this then. No, that's not what I wanted. Ah. Okay, so we're almost there. I think there's a couple of things that are still not quite right here. First of all, if I type here, nothing's coming out. So we need to fix that. That should be pretty easy by now. So we already have our little loop here, and we might as well start from 4 like someone suggested. And then we'll just write this out to all of them.
So now we have to do a strict less than, right?
Why is that? Then we're going to miss one again. But the starting at 4 doesn't matter. It wouldn't have run at all before. But max time was 4. So if you start at 4 and you say less than 4, it's not going to run. But the thing is, max time was 4 and we were starting at 3. So we were checking 3, which was the server socket, and which was pointless. Okay, so let's see. So now I'm using this. I don't want to write to sockets that aren't in use. That'll be kind of silly. And maybe it'll even create some error. So I'll just check in the, not in the ready set, but in the read set. See if we're still trying to get something from them. In that case, it's probably ready to write to as well. So we'll go for that. We could if we wanted, but it's going to get a lot more complicated. We could put a write set here and say, oh, I want to write to this client. Right? Then wait for the client to be ready to write to. And it's probably always going to be ready to write to. But that's important if we're trying to write a lot to a client. If we're trying to write megabytes to a client, it's not going to be ready after a while. So then the writing is going to be a blocking factor. If you try to write without the client being ready, it's going to just stop and then everything slows down again. So what we're doing here is we're just assuming that it's going to be ready. But if we can't assume that, in this case we can. If we can't assume that, then we need to have a write set as well, if we want things to be fast. Okay, so let's just write to it. Go like that. Now we got a hello on both ends. Okay, so it's not quite a chat server yet, right? But I think we'll stop it here. So the remaining piece, I suppose, at least for an what do we call it? A party line, is if I type here, it should really come out here too, right? One client says something, it should come out at all the clients. But it's really not going to be a big difference. It's basically the same thing here. I would break this out into a little function, right? So I don't have to copy paste the code, and then just say write to all, right, for every message that comes in, and that'll be good to go. Okay, so this is your chance here to make sure that you really understand select. So any questions on what we just did here? Oh, okay.
What was
Yeah.
the done annotation advantageous to not use sockets, or not advantageous to use sockets. That's like threads.
Why would it not be advantageous to use threads? Yeah, starting a thread takes a long time. Not by disk standards, but it'll still take on the order of dozens of microseconds. If you have lots of connections coming in, you don't want to waste time on that. You also don't want to waste resources. A thread uses a lot of memory and a lot of state in the OS. If you have lots of ongoing connections, not 10, but if you have 1,000 ongoing connections, or 100,000 ongoing connections, that you can easily do with select. We'll have to figure out how to deal with file descriptors larger than 1024. But you can't have 100,000 threads on a normal machine. It's going to go crazy. And maybe let's think about what the advantage would be of having threads instead. You think, why would anyone want to do threads when you can write it with select?
You get more resources for each thread, like you don't have one process between client and server with each individual thread. You have like control.
You get more resources. What kind of resources?
Like being able to. I'm not sure what to do.
There's one resource that you get. Sometimes you get a lot more of if you use more threads. CPU, yeah. The reason being, you can only run a single thread on a single core. In modern machines, you have more than one core, and your program will be stuck on one. So if you want something to run really fast, what you should do is first implement it with select, because that's by far the most efficient way to do it. And then you have to multi-thread it, so you have one thread per core, all running select, and then you'll most likely get the most efficient solution. Now, the main advantage of doing something with threads is that it's really easy to see what's going on. Reading this code is kind of hairy. Reason being, we have, first we have the mixed in here. We have the server socket, we have this other thing we're reading from, we have a bunch of different clients. There's just stuff happening in random order all the time. If you have threads, it's just one loop, and it's all about one client. So it makes it really easy to read. Unfortunately, it also makes it really hard, as we'll find out in the rest of this class. It also makes it really hard to understand exactly what's going to happen. Because with threads, you get what's called non-determinism. So depending on scheduling of events, depending on when the user types something, things will execute in different order, and you may get all sorts of weird behaviors. Yeah?
Would this handle like 1,000 clients?
Yeah, this would be no problem at all with 1,000 clients. It actually works right now with 1,000 clients.
Does it just go into like a buffer?
There's no buffer really. So you see, all that happens here is we're waiting for whoever's in the ready. Oh, actually, it only works with 32 right now. Let's make it work with 1,000. There. Oh. All right. So all it does is it waits for all of those different sockets, right? As soon as something is ready, it'll read from it and move on. So, okay, so maybe here, one weakness. Yeah. So if you have 100,000 clients here, we're looping through up to max client every time. That seems like a weakness. So there are faster ways to traverse. So say there's only one client ready. Right? Now we're going 1,000 times, 100,000 times around this loop to find that one client doing this if set all the time. There are faster ways to find which client is ready. In this bit set, you can do it. Like there's faster ways to check a bit set or a bit array for set bits. But they're not that much faster. And there's another system called poll that's basically the same thing, but a little more clever. That would probably be better if we have very large number of clients. That's a good question. Other? Actually, let's take a look. I don't know if poll is available on OS X. Oh, here we go.
Huh.
We have something we need to fix. This is no good. Any idea what happened?
We closed down.
It ended up closing the socket on the server.
Yeah. So the client closed the socket, which means over here we read something, but we got 0. This is poorly indented. And we got a 0, and we ignored it. So the 0 means the socket got closed. So now, next time we go around, select says, yeah, this socket still has something to tell you. Right? It's closed. And it keeps happening over and over. And we tell select, well, is there anything new about this socket? And then it says, yeah, it's closed. And, yeah. So we gotta, if it's closed, we're not interested in it anymore. We have to tell select that we're not interested. So we have to clear this one. We'll say, if receive len equals 0, then we'll clear it. C from read set. That should take care of it. Okay. All right. So now everyone's calm. And let's see if we can get back in. Number 6 we got. So I suppose we keep using new file descriptors.
We could be closing them now.
Oh, we didn't close it, yeah. Maybe that'll help. Probably that'll help. Let's fix that too. We're getting pretty close to a solid chat server here. Huh. Yep. We're getting 5 back every time. Okay, so looks like that's about it then.
If you close 4, will it, because 5 is at the end of the list.
Ah, let's try it. I suspect we'll get 4 back, yeah. Other select questions? Yeah, so what I was going to do here is look for poll. Huh. This doesn't look any more clever. Oh, does it say which one? You know, I've never used poll. Actually, seems like a weakness. So I'll have to look this up to see how we do if you have a ridiculous number of file descriptors. How do you figure out which one is ready out of so many? Because with select, we have to run through the whole thing. There ought to be a better way. Okay, so I suppose that's it for select for now then. So your web proxy that we're doing for homework is going to be select based. Haven't decided yet if we'll also do one that's based on fork, but we'll see. So there's 3 different ways of doing multiple clients, right? There's the select, there's forking, in which case you make a new process of yourself, right, and handle it separately, and then there's threads. We haven't really talked about threads yet, but with threads, you're not a separate program. You have a separate stack, but you have the same heap as all the other threads in the program. And that's probably the most powerful abstraction, but also by far the most complicated. Okay, so let's take a quick look at email then. And we'll need a drawing. So we are not going to talk about Gmail here. Gmail is, or any webmail like this, is a centralized sort of weird corner case of email. It works fine, but it doesn't work the way email was designed to work, at least. So we'll look at it. For starters, we'll look at least at how it was designed to work. So here's my mail client. Who here uses a mail client? That's it. Everyone else is on Gmail? Okay. So a mail client looks something like this. It is, of course, vastly superior to Gmail. It's a local program that runs on your local machine. It has all your email even though you don't have an internet connection and such things. It's a very nice service to have. And it works with Gmail if you want. Now, this is my mail client. It runs on my machine. If I want to send an email, then the question is what happens. Right? So I want to send an email now, email to somewhere at mit.edu, let's say. Actually, let's say I'm somewhere else. I'll send it to uic.edu. To Jacob at uic.edu, in fact. All right. So how do we figure out now where to go next? There's a server in between here. Anyone want to come up with an acronym? It's an outgoing mail server. But
it's not SMTP.
exactly. So SMTP, Simple Mail Transfer Protocol, outgoing. Okay, so the mail client is configured to use an SMTP server, and that's going to be on the local campus. Now we're on somewhere else. So we're using whatever my internet provider is offering me. If I'm at home or if I'm in a company, the company runs their own SMTP outgoing email server. Okay, but that's within the company, and we're trying to go somewhere else now. So actually, to make this, to stop confusing things, we'll say we're now at MIT. Okay, and they're trying to email me. Okay, so the next step now is for this server to figure out who should it send it to. So these emails, I don't go and fetch email from MIT's SMTP server. That's clearly not what happens. In fact, on my end, I have another mail client now. On my end, I'm probably reading this from an IMAP server incoming. Okay, so now the question is, how do you get an email from here to there? So how does the MIT even know where to send it? Any thoughts? They need to contact some mail server over at UIC. In fact, there's a separate one called SMTP incoming here. So any thoughts on how they would find, like, what is this server?
I assume it would be listed underneath the name server.
Listed underneath the name server. Yeah, okay.
Similar way you find any.
Yeah, exactly. So if you want to find a computer in general, find the address of any computer, you use, in this case, we type host, but you use DNS, like you said, to figure out the address of it. So if I say google.com, I get an IP address. Oh, actually, now I got both there. So if I say type address, I get a bunch of addresses that all correspond to that name. But if I say type MX, that's a mail exchange, now I get some mail servers instead. So let's do that for UIC. Okay, so there are two mail servers that we can talk to deliver mail into UIC. Let's try that.
10 is the fourth.
No, it's a priority. It's like they prefer that you use these two. Here, Google, they prefer that you use this one, but you can use these if the top one doesn't respond. Okay, so that's the incoming mail server for UIC over here. So now the outgoing mail server connects to the incoming mail server and transfers the email. Now, I don't have to be a server to do that. You can also be a computer science major. So we'll talk to it directly. Why not use NC? That's the machine. Port 25 is where SMTP listens. So any SMTP server is going to be running port 25. There's the SMTP server. So I'll say mail from Jacob at sale. Actually, no, let's not do that. Oh, what happened? Hello. Okay, let me try this with Telnet. There seems to be a problem with the line endings. You have to say hello first sometimes to be polite. No? Okay. It's all these syntax errors here. This actually works. Hello. Oh. Okay.
What protocol is this? SMTP?
This is SMTP. It's very polite. And this is who should get it, or I keep forgetting about the angle brackets. Damn it! Ah!
And there's no command.
There we go. Okay, and now we can send some data. So I'll say okay, so there we are. Let's see if we got some email.
Can we do it to anyone?
Ah, look, Obama's mailing me. All right. So, as we can tell, there is no authentication whatsoever in email. You have to fill out all these passwords, right? When you're at least when you're setting up your mail client, there's all these passwords. There's SMTP passwords, IMAP password. There's all this stuff, but it doesn't actually do anything because if you look here, this link can be authenticated, and this link can be authenticated. So here you have a password to read my email. You have to have a password, and that's a very good thing. I wouldn't want just anyone to be able to read my email. In order to connect to this server, sometimes servers will be a little paranoid. So they will say, oh, well, I'm not going to just forward email for anyone. It's only going to be the employees of this company. Good reasons, right? Because otherwise spammers would connect to your server and use your server to send millions of emails to the wrong place. Okay, so that's also authenticated. But then this part here, there's no username and password. Any idea why?
How would the other server, like the receiving server, be able to opt in? Like if they had a username, that's fine.
Yeah, so the problem is this server can send email to anyone in the whole world. There's millions of these servers. What kind of username and password are we going to have? Are we going to have the username and the password of the recipient? Hardly, right? No one's going to have my password. They can have my username, but that's okay. They're not going to have my password. So that doesn't work. What about the sender? No, we have 4 billion different senders. You're not going to have 4 billion different accounts on this SMTP server. That doesn't work. How about the server? So now you're going to have, so maybe you can have this server having an account on this server, and so then they can talk to each other. That would work, but it's still an enormous headache to get all these millions of servers to all know about each other and keeping everything up to date and so on. Doesn't really happen. So that's the current state of email. There's no authentication. Anyone can send email as anyone else. So be a little careful when you read your emails, or at least when you respond to them. There's another piece there. There's also no encryption. So this part can be encrypted, oftentimes with SSL, nice, good crypto. Same thing here, very nicely encrypted. This thing here, nope, there's no encryption.
But these encrypted data itself, you would expect the receiver to know how to read it.
You could do end-to-end encryption with PGP, pretty good privacy, that sort of thing. You can, on your mail client, you can encrypt it, and the other mail client can decrypt it, assuming you've set up password, set up encryption keys and so on. I've tried it. It's an enormous headache, and it doesn't work out. After a few months, it was just I had to shut it down because I was losing email left and right. Okay, so this is also unencrypted. It's encrypted to your SMTP server if you're lucky, but between them it's not. So organizations, government organizations perhaps, that would be interested in reading email, all they have to do is tap into some big pipes, all right, anywhere where there's lots of internet traffic going on, and they will see everyone's email in plain text.
Is it possible for any of us to go into those pipes?
That's a good question, right? So for the NSA, it's trivial. You threaten people with jail time, secret courts, that sort of thing. For us, it's hard. So these pipes, they're not really pipes, right? What are they? They're either copper cables or they're optical fiber, almost all the time. So these are very hard to get into. In order to get access, you actually have to break into a room or something like that. Or you can sometimes maybe subvert a router. So you can hack these routers, they might have buggy firmware. You can maybe find a bug there and you run your own software on it and that sort of thing. But it's hard to get access to these pipes.
It's not possible to spoof myself as the incoming server.
No, it's very hard to trick traffic to go to the wrong place as an end user. If you are an ISP, you can sometimes do it, because, well, you'll find out in 450 as well. There's also no authentication in the routing system for the whole world. At some point, Pakistan managed to shut down YouTube for the entire internet. Because they said, yeah, we got YouTube over here. It's the closest route, so everyone sent their requests to there, and yeah. So there's a lot of trouble there. Anyway, this link is hard to get onto. You have to be an ISP, you have to be a government agency, something like that, usually. This, though, is very easy to get onto. So if this part is unencrypted, why is this easy to get onto? What can you do to read on this link? Speak up a little bit. Yes, okay, so if you're sitting on the same cable, you're connected with the same cables to the network, there's easy ways to start sniffing traffic from the network. But there's some other technology that we all use that makes it even easier. Wi-Fi. Alright, so you go to Starbucks, you use their free Wi-Fi, this is unencrypted. So now you're using unencrypted link to talk to your ISP's mail server or whatever. And some other guy is sitting next to you, and he can read it. As long as you don't encrypt this part, then he can read exactly what you're sending as well. So it's somewhat easier. You have to be next to the person sending the email, but it's not so bad. The same thing here, right? Reading on that end too. So in general, one should treat email as what are they called? Postcard. Right? It's not a letter. Encrypted email is like a letter. The NSA, they can still open it because they know how to decrypt all of email. They'll figure it out. So they can open the email and you'll never know. But or open the encrypted stuff. But then for everyone else's regular email, it's like sending a postcard through the mail. So the mail carrier, which is the ISP, can easily read all of your stuff, like trivially. He's got this pile of cards and he's just reading it. Right? So you don't want to send in sensitive information over email for this very reason. You can't trust the carriers or anyone along the way with real secrets. With things that are not so secret, you can, of course, encrypt it, and then send it. If it's not very secret, encrypt it and send it, and then hope that no one opens it, because it's a hassle to open it, and maybe you'll find it out, and then, of course it's illegal. So encrypted email is probably pretty okay. But if it's a real secret, of course, you don't put it on a computer at all. We learned why a few times. Okay, so that's it for today. And I'll see you on Wednesday, and I'll post the homework tonight, I think.